following specifications, total output offset voltage is equals to 479 millivolts. Input offset voltage is 4 millivolts. Find the input offset current. Here feedback resistance is 500 kilo ohms. Here total output offset voltage is equals to input offset voltage multiply with gain, that is 1 plus RF by R1 plus input offset current into feedback resistance. Here input offset voltage is given as, means if we compute this portion, that is 4 millivolts 1 plus 500 by 5, which is nothing but 404 millivolts, means output offset voltage because of input offset voltage is nothing but 404 out of 479. So the offset output voltage contributed by the input offset current is this one, that is IIO into RF is equals to 75 millivolts. So input offset current is nothing but 75 into 10 power minus 3 divided by 500 into 10 power minus 3. So 150 nano ohms is the input offset current, hence option B is correct.
Characteristics of different relays are shown below. Match the following. Okay, there are different operating characteristics given and named it as 1, 2 and 3. Now we have to match the 1, 2, 3 characteristics with these 4 types of relays. So first characteristics is, if you see here, this x-axis and y-axis is almost change is constant. Okay, this is called a definite time relay. So one is S. If you see operational characteristics 3 here, it's almost inverse. So this is 3 is P. Okay. What about 2 characteristics? 2 is equal to inverse plus definite time relay. So this is inverse definite minimum time relay, that is Q, IDMT. So S is 1, P is 3, whereas Q is 2. Okay, this is the option. Correct answer.
E power Z is equals to 1 plus I. Find the value of Z. Here Z we can write as x plus Iy. So e power Z is nothing but e power x plus Iy. So e power x into e power Iy. So e power x, e power Iy can be replaced with cos y plus I sin y is equals to 1 plus I. If we compare LHS and RHS equations, then we will get it as Ex cos y as 1 and Ex sin y is equals to 1. So we have to decide the values for x and y. So in order to decide the value for x, we have to remove the variable y. So we have to square these two equations, that is this one and this one, and add together, that is Ex cos y whole square Ex sin y whole square is equals to 2. So e power 2x is equals to 2. So x is nothing but 1 by 2 natural logarithm of 2. Similarly, we can solve for y, that is tan y is equals to 1. So y is nothing but pi by 4 plus n pi. Hence z is nothing but x plus iy 1 by 2 natural logarithm of 2 plus I n, that is pi by 4 plus n pi Hence option C is correct. MOSFET can be modeled as an ideal voltage controlled current source as shown below. The control source is defined by I2 is equals to 2.5 V1 milliamps. So, as per the data, the I2 depends upon the value of V1. So, for the output pulse sequence, that is V2 is given as follows, that is 10, 0, 10, 10, 0 ohms. Means this is the sequence which we are getting for V2. So, here V2 is decided by the I2, that is, we can write V2 is nothing but 10 minus 2k into I2. So, if we substitute 2.5, 10 minus 5V1 is nothing but a V2. Whenever V2 is equals to 10, if V2 is equals to 10, V1 is equals to 0. V2 is equals to 0 means V1 is equals to 2. So the sequence which we are getting here is 0, 2, 0, 2, that is option A is correct.
Having 15% reactors are interconnected through a tie bar reactance as shown in figure. Okay, calculate the fault impedance if three-phase fault occurs on any of these generator bus. Let us take the fault occurs on this generator bus. This is the fault point. Now what is the reactance diagram here? The reactance diagram for this generator bus is like this. This is die bar reactance of 15%. This one is generator reactance is of 15%. It is drawn between phase and neutral. Okay, and another tie bar reactance of 15%, and one more is generator reactance is of 15%. Now fault occurs at this point. We have taken it at. Now what is the fault equivalent? XF is equal to, okay, this comes into picture parallel to that of this 15 ohms. So this is 15 plus 15 plus 15, that is 45% is in parallel with 15% reactance. So 45 into 15 by 60, which is equal to 11.25%. That is option C is the correct answer. Resistance type relays are more sensitive than that of induction disc type relays. Okay, this option is, this one statement is true. Okay, induction capacitance relays are more sensitive when compared to induction disc type relays, because induction disc type relays, the construction is different. Okay, when you have two types of torques, there will be some time to rotate the disc, okay, because of the friction. But induction capacitance type relays, we don't have any friction. So if you give very less input, okay, there will be a good amount of deflection. That's why it is saying induction capacitance type relays are more sensitive. Okay, one is true. Now capacitance type relays are used in high speed relay applications. Because these are more sensitive, we should use in high speed relay applications. So this is also a true. So option B is the correct answer.